the idea will be to get these vertex operators, but now in a language which is manifestly 10-dimensional space-time supersymmetric. So one wants to find vertex operators V satisfying QV equals 0. And if we're looking at the massless sector, it's just going to involve x's and thetas, but not derivatives of x's and thetas. So you might be a little bit confused because in the RNS description, the vertex operators for the massless sector had derivatives on the x's. But it's because in this formalism there's a tachyon. So if you didn't have any derivatives, you'd be describing the tachyon. In this description here, there's no tachyon. So the vertex operators with no derivatives describe the massless sector. Now, if we're doing the open string theory, the vertex operators should have ghost number 1. That's because, as in bosonic string theory, if you remember correctly, there was a C ghost associated with fixing the location. So if we're describing the vertex operators which are fixed for the tree amplitudes, the ones which are not integrated, they should have ghost number 1, which in this case means that they are linear in lambda. So this is the most general thing you can construct, which is linear in lambda and doesn't depend on any derivatives of x or theta. And it involves this spinor field A alpha. And QV equals 0. Q is just lambda alpha times d alpha. And d alpha, if you take the OPE of d alpha with the vertex operator, you just capital D alpha V, where capital D alpha is just the usual 10-dimensional supersymmetric derivative. So this is easy to see just by looking at small d alpha. And remember that small p alpha is the same as like dd theta, and dx is like ddx. So ddz of x acts like the conjugate to x, so ddx. The third term in d alpha doesn't do anything if it only acts on a function of x and theta. Okay, so the equation we're looking for is that lambda alpha now this is a bispinor, and in 10 dimensions, a bispinor can be expanded in terms of a 1 form and a 5 form. So the 1 form is, of course, proportional to lambda gamma m lambda. So there's some coefficient in front that I'm ignoring. And the 5 form is proportional to lambda with 5. Now this is vanishing for a pure spinor. So saying that this is 0 just implies that if you contract these indices with the 5 form, it must vanish. So QV equals 0 implies that this supersymmetric derivative of this superfield must vanish. And furthermore, it cannot be BRST trivial. So the BRST trivial variation of V is Q of omega. And now again, because d alpha just acts in this way, this is just equal to lambda alpha d alpha of omega. So the gauge symmetry of A alpha is just so being in the cohomology implies that this A alpha satisfies this equation and is defined up to this gauge transformation. Now these are precisely the gauge transformations and equations for d equals 10 super Yang-Mills. Or more precisely, to linearized level, d equals 10 super Yang-Mills. So the way to understand that is if you define a covariant derivative in the same way as one defines a covariant derivative for ordinary Yang-Mills, so this would be the spinor version of the covariant derivative, then one can show that these two definitions define gauge fields for super Yang-Mills, so A alpha and AM, and the relation that del alpha, del beta this relation here, which is of course manifest if A alpha and AM are 0, that's just the same relation as I wrote down here above. If you introduce these gauge superfields and request that this is preserved, then in fact it precisely implies these equations and gauge invariances. So let me sketch how that works. So I don't know, can people, no. Okay, I guess it's too late, but can people see on both sides of these? So, okay, so all right. Yeah, that I figured out. Okay, I can write bigger. Should I just not use this? Well, it's too late for you guys. But okay, so half of you can follow this part. Okay, so okay, so this equation here yes, so it turns out that when you have a maximally supersymmetric theory, you can write down the on-shell equations in first order form. That's right, it's related to the fact that it's BPS. So let me show you that that equation implies the equations of motion that I claimed. So this equation here, remember, is d alpha plus so to linearize level, of course, there's a quadratic term, and if you're doing the full nonlinear term, you need this also. But to linearize level, this is of course equal to d alpha a beta, just symmetrized in alpha and beta. Now, as we already mentioned, this can be expanded in terms of a 1 form and 5 form. This is equal to gamma m. And the 5 form part. Now, what this equation tells me is that the 1 form part is equal to AM. So the equation is that AM is just this piece here. And that the 5 form part is 0. So this equation here is just a definition for AM in terms of A alpha. So although the vertex operator is just written in terms of A alpha, this superfield here, the equations of motion imply that AM is determined in terms of A alpha. Furthermore, this equation here implies that the 5 form part of the derivative of A is 0. Okay, so we've seen that this equation here implies that this vertex operator precisely describes on-shell super Yang-Mills. And of course, the gauge symmetries are manifest. So the gauge transformations are delta A alpha is d alpha of omega, and delta AM is dm of omega. So these are the linearized gauge transformations. And as we see, A alpha just transforms in the desired way under the gauge transformation. So if you expand out A alpha to see where the physical super Yang-Mills field, what you find is that using this gauge transformation, you can gauge away the term which is lowest order in theta, and you find the term which is linear in theta, is just proportional to the usual gluon. And the term which is quadratic in theta is proportional to the gluino. So this psi AM and psi beta are the glue on-shell super Yang-Mills fields. The terms which are higher order in theta, so the terms which are order theta cubed, for example, they're going to be proportional to the derivative of the gluon. And theta fourth will be proportional to the derivative of the gluino, and etc. If you go to theta fifth, it will have two derivatives on A, but everything will be determined just in terms of these fields. So the precise dependence here you just obtain by requiring that A satisfies this equation. Okay, so this is the proof that the cohomology, at least at the massless sector, correctly describes D equals 10 linearized super Yang-Mills. Okay. Nothing. So we can put any Chan-Payton factors here we want for the open string. And at the cohomology level, it doesn't tell you anything. Now, of course, consistency of the amplitudes will put restrictions on the gauge group. But the cohomology does not tell you anything about the gauge group. So I could have just U1, I could have whatever. Right. It's also true for bosonic string and RNS. You don't get any information from. So it's just linearized level, so there's no hope of getting. Yes. So you're asking if this has some relation to self-duality. Yeah, so 10-dimensional is a little bit off subject, but I'm happy to go there. So if you reduce to 4 dimensions, so you have n equals 4, D equals 4 super Yang-Mills. There's a term, so this has 6 scalars in it. And when you expand these superfields, you find that both the 6 scalars and the complex conjugate appear. And that equation, if you dimensionally reduce it, is going to give you a relation between phi and phi bar of this form, like with a factor of a half or a fourth, something like that. So this is very similar to self-duality. If you were in, the self-dual equations for self-dual Yang-Mills are something like this. It's phi alpha dot beta dot equals 0, something like that. Or phi 1, okay, I'm not making it obvious, but this is certainly related to this. Okay. Yes? Yes, so this is just to linearized level. So if you work to nonlinear level, you'd see the extra term. Any other questions? Okay, so that was relatively simple, and now let's do supergravity. So you might be scared that things are going to get complicated, but in fact, things don't get more complicated. For the closed, now you both have left movers and right movers. So if we're doing type 2, this is just the left moving part of the action, but you'll also have a right moving part. And I guess, sorry, at some point I put a tilde to be projected, but I'm just going to take that away. So you have a right moving sector also, which is and if we're doing the closed string, the vertex operators which are at fixed locations should have ghost number 2, with one left moving and one right moving ghost. So again, this is the only thing you can write down. And now if you impose that both Q and Q hat annihilate V, then you find that this is precisely the description of type 2 supergravity. So let me write this in this form. So it's like the left moving, right moving, I guess, squared. So if you expand this superfield, what you'll find is that the G plus B plus 5 field, they sit at order theta theta hat. So that's analogous to what happened here when we take the left-right product of two of these. So these are the fields that we knew how to do in RNS, but now we can get the Dilatinos and the Ramon-Ramon field. So the Dilatinos would sit, for example, at order theta squared theta hat. This would sit at theta hat squared theta. And the Ramon-Ramon fields, which we had such a big problem in describing using RNS, these sit at order theta squared theta hat squared. So you'll get F alpha alpha hat times I guess I have too many hats, so this is beta beta hat. So you see the vertex operator involves all of the fields in the type 2b supergravity spectrum and in a uniform way. So in that sense, it's much nicer than in RNS. Okay, this is for the vertex operators which are at fixed locations. The next thing we want to do is to describe this superstring in curved backgrounds. So in RNS, remember, we didn't have these theta variables, we had psi's. So there was nothing you could use in a natural way to construct a space-time spinner. So there are unnatural things to do, which you bosonize the psi's and then construct spin fields, and that's what Friedan, Martin, and Schenker did. But that requires the Wiltshire ghosts, and it's not manifestly space-time supersymmetric. So it's crucial that you have these theta variables in order to construct them. Okay, so okay, we want to get to this formula. So I have to tell you what the analog of these integrated vertex operators are. So the integrated vertex operators are going to have ghost number 0, and they're going to be related to these unintegrated, but the relation is a little bit, let me call this U, just so, for unintegrated. The relation is going to be, so Q of U is of course equal to 0, and U is not BRST trivial. But suppose we take a derivative of U. So of course Q of du is of course 0 still. So this is now a dimension 1 operator. But in this case, U is BRST trivial. And it's going to be the BRST variation of a dimension 1 operator. And this is defined to be the integrated vertex operator. This is the object which you're going to integrate in order to define the genus G scattering up. if we do for the closed string, this is the object whose integrated version is going to give me the action in a curved background. Okay, so yes? Yes? So I'm going to have to tell you where this comes from. So I haven't told you what this B ghost is yet. I'm going to get there. Okay, so let me tell you what it is. So what we have is a BRST. So let's turn the question around. Suppose somebody gives you a string theory which is gauge fixed, together with a BRST operator. So we want to define scattering amplitudes which are BRST invariant. So what are the rules? So let me tell you what the rules are. So first one needs to define what the physical vertex operators are. So those are the states which are in the cohomology of the BRST operator. Now you have cohomology at dimension 0. These are the fixed vertex operators. And these are the integrated vertex operators. So the integrated vertex operators are obtained. They're not supposed to be BRST invariant. They're supposed to be BRST invariant up to its whole derivative. And this should have been du. So that's the definition of the integrated vertex operator. That's also true in bosonic string theory. So in bosonic string theory, U is equal to, let's do the massless case. Now if you take D of U, that's of course equal to D of C. You can write this as Q of dxm am. So if this is your definition of the unintegrated, then the integrated is just defined to be V. So this is now in bosonic string theory, there's an easy way to get from V to U. You just pull off the C ghost. So I don't have to use this in order to relate U and V. In this formalism, we don't have a C ghost. We have these lambda ghosts. But we have the BRST operator, so we can use this same prescription to define the relation between U and V. We don't need the C ghost in order to define the relation between unintegrated and integrated vertex operators. Okay, so let me tell you what let me tell you now what the B ghost is, and that may help to understand the relation. So the B ghost in bosonic string theory and RNS string theory and this string theory also is going to be defined such that it satisfies this relation where T is the stress tensor. So if you remember, the C ghost is just the anti-ghost the conjugate goes to B. So in the same way that this B ghost, this relation here is crucial for understanding why the B ghost appears here. It's because it's when you vary the conformal moduli, it's related to a transformation related to T. So this relation here tells you why the B ghost sits here. And the inverse is also true. So the fact that Q with B is equal to T says that if you have CV, then Q of CV is going to be related to is going to be related to D of V. It's the same type of relation because the B kills the C and the T acts with this derivative here. So this is in fact a more general way, without involving the C ghost, of understanding these insertions and also the relation of U and V. Okay, so I think it's a correct statement that the C ghost is not necessary in order to define scattering amplitudes. You do need the B ghost, but this is enough in order to discuss the prescription. Okay, so what can I say? So using this definition of the B ghost, I can prove that this prescription here is BRST invariant. Now you might ask, is there an alternative BRST invariant prescription which gives the scattering amplitude? And that, okay, I can't prove this is the only prescription which makes sense, but I think it's reasonable to assume that BRST invariance uniquely fixes the prescription. This Q is the same Q as here. This Q is the Q that I'm going to use in order to define physical states. I haven't found B yet. Okay, I'll tell you what B is soon. But this is going to be the definition of B, that's right. And then if you plug that definition into here, it gives you a prescription for the scattering amplitude. Okay, so let's go back to tree amplitudes. So it's easy to show that this is a conformally invariant prescription. Oh, times this Z, let's put the C's in. So this is a conformally invariant prescription. Now why is this a BRST invariant prescription? Well, it needs to have certain properties. It needs to have the property that obviously the Q of CV has to be equal 0. And it has to have the property that this object here, Q of V, it doesn't have to be 0, but it has to be a total derivative. A total derivative of what? Well, this expression here should be invariant under cyclic permutations. It shouldn't matter which one of these is integrated and which ones are unintegrated. So obviously there should be a relation between these and these. So let's call, instead of writing it CV, let's write this as U, just to use the notation I'm advocating now. So in order for this to be invariant, Q of U must be equal 0, and Q of V must be a total derivative. But in order for this to be cyclically symmetric in the sense that it doesn't matter which ones you chose to be U's and V's, the relation has to be of this type. That Q of V has to be the derivative of U, and using this relation you can show that, that this prescription is equivalent to this one, for example. U1, U2, so you can show that this is equivalent to this. You essentially use a BRST, okay. The way you prove this is you write U is equal to the integral of du, which is equal to the integral of qv. And then you pull the q off of this, and it turns this expression into this expression. Okay, so this relation here is crucial for this to be invariant under cyclic permutation. Okay, so that's the tree amplitude. And of course, there's similar requirements for this expression to be consistent. Okay, so all I'm doing is rewriting the bosonic string amplitude prescription without explicitly writing the C ghost. So I'm just using these U's and V's. Any other questions? Okay, for people who have studied topological amplitudes, it's a similar game. So in topological string theory, you're usually not given a B and C ghost. You're just given a BRST operator, and you're asked to compute what are the BRST invariant amplitudes you can construct. Okay, so what we're going to do is construct this B ghost, but first we're going to construct these integrated vertex operators. So the things I'm calling V. Sorry, which one are we talking about now? On this board or on the other board? On the top board? Data, yes? Certainly not in a covariant way. I don't know how to do it. You can try to do it in a non-covariant way, and in fact, that's the way this system was derived. But in a covariant way, I don't know how to do it. Okay, so let's now construct what V is. So we constructed what U is, and it's very simple. Now remember, in RNS, V was a little bit more complicated. It had the term here, but it also had a term proportional to the field strength. In this formalism also, V will be slightly more complicated. So we're going to require that Q of V is equal to the derivative of lambda alpha A alpha for the massless case. So this is what U is. So what you find is that V starts out with d theta alpha A alpha. Then there's a term proportional to AM, the same AM that appeared here. And then you get terms proportional to the strength, just like you have terms proportional to the field strength here. So the field strength for super Yang-Mills comes in two different forms. You have a spinor field strength which starts with the gluino, and that turns out to couple to d alpha, the same d alpha that appeared here. And finally, you get the coupling to the ghosts, which is of this form. So this vertex operator has the form that if you act with it on Q, you don't get 0, but you get a total derivative of lambda alpha A alpha. If you expand in theta, so these are all superfields which depend on x and theta. If you expand in theta and just keep the terms with lowest order in theta, you'll get something which looks very much like this. This is equal to lowest order in theta. It has a term of this type, and then it has a term of this type. So it has the usual coupling of dx to a. That, of course, comes from here. Pi m is defined on this board. It's dx. Oh, I erased it, sorry. Pi m is just a space-time supersymmetric version of that. So that contributes this term here. And this term here gets a contribution from here because the gluino superfield has as its theta component the field strength. And of course the contribution from here and so on. And you see this is related to the Lorentz current that I discussed earlier for RNS. So the fact that this has the same level as this is crucial for the scattering amplitudes to agree. Okay, so it's a little bit more complicated than RNS, but it has the advantage of being manifestly space-time supersymmetric. You can write it in terms of these superfields. And for tree amplitudes, you can explicitly compute the expression. So for tree amplitudes for Neuer-Schwarz states, of course, the answer has been known for 40 years using RNS. But for Raman scattering, if you're computing scattering of fermions, using RNS, it's only been computed up to 6 fermions. Nobody's ever computed using RNS beyond 6 fermions, just because the fermionic vertex operators are so complicated. But in this language, you can compute arbitrary numbers of bosons and fermions. And in fact, recently, Marfo and Schlotterer wrote down explicit expressions for arbitrary numbers of external states, super Yang-Mills. So this is the most efficient method for tree amplitudes. And now for loop amplitudes, there's one more object you have to introduce, which is this B ghost. So this is the most messy part of the formalism. So this is the part which hopefully can be understood better in the future, but at the moment, it's just a computation. So we know what Q is. We know what T is. So T is just the stress tensor, which is equal to dx dx plus p d theta plus w d lambda. And now we have to work hard and construct what B is. So it's a cohomology problem. We just have to find an operator which satisfies this identity. And what you find is that B cannot be constructed in a manifestly Lorentz invariant way unless you introduce what's a pure spinor of the opposite chirality to lambda. So let me write down the expression and then I'll explain a little bit. So I don't want to go into too much detail on this because I'll run out of time. But let me say some of the features of this B-ghost. So the B-ghost it's manifestly space-time supersymmetric. It satisfies the property that Q with B is T. But it has a strange feature that you have to divide by a factor of lambda, lambda bar. So lambda bar is a pure spinor of the opposite chirality to lambda alpha. And there are two ways to treat it. One way is to treat it as a fixed spinor, and then it violates Lorentz covariance, at least manifest Lorentz covariance. The other way, which is called non-minimal pure spinor formalism, is to think of lambda bar as an independent worldsheet variable. Now, if you do that, you have to add it to the action here. It has the opposite chirality to lambda. So if lambda has an up index, lambda bar has a down index. If you're doing the closed string, you also need the left moving version. And in order that it doesn't affect the central charge or the level of the Lorentz current, you have to introduce also a fermion. So the opposite statistics, so that it cancels the contribution to the central charge into the Lorentz algebra. So this lambda bar is a pure spinor like lambda, so it satisfies this identity here. And the fermion that goes with it is also a constrained spinor. So this implies that lambda bar has 11 independent components. And similarly, R has 11 independent components. So because these are bosons and these are fermions, they contribute with opposite contribution to the central charge. And if you want that they don't contribute to the cohomology, that's what I'm doing right now. So you have to add a term to Q, which is W bar alpha R alpha. So this tells you that they don't contribute to the cohomology. So with this modification, which is called non-minimal pure spinor formalism, you can now construct the B-ghost. So the B-ghost is, this dot, dot, dot is going to include terms which depend on R. And it's explicitly written down. I'm just not writing it because it would take a few lines. Now when you do the path integral here, in this correlation function, you of course have to do a path integral not just over the x's and the thetas, you also have to do a path integral over the lambdas and lambda bars and these r's. Okay? And this is what was explicitly done, at least up to 3-loop 4-point amplitude. So the advantage of these computations is that space-time supersymmetry is manifest. So if you had done this computation in RNS, I didn't mention this. In RNS, you would have had to also sum over spin structure. So in RNS, of course, these psi variables in RNS, because they're spin 1/2 on the world sheet, they carry spin structure. And the scattering amplitude is only space-time supersymmetric after you sum over spin structure. In this description here, all of the variables have integer conformal weight. So these are conformal weight 0. The lambdas and lambda bars are also conformal weight 0. So what that means is that there's no spin structures. So the expression you get is just a single expression. You don't have to do a sum in order to get the space-time supersymmetric answer. So for example, at 2 loops, if you try to do the 2-loop amplitude, so this was done in RNS by Doker and Fong, it takes hundreds of pages to do the sum over spin structures, whereas in this formalism, it's just a 4 or 5-page computation. Okay, so this is a summary of what can be done in multi-loop amplitude. So the next thing I wanted to do was say briefly about curved backgrounds, but are there any questions before I go to the curved background? So okay, so let's suppose we understood the first part with the lambdas. And now you want to add some new degrees of freedom. So yeah, so you can write, if you want, you can think of this as coming from gauge fixing. So okay, at the moment I don't remember the simplest way to do this, but this is the standard quartet mechanism. So to any conformal field theory, you can always add a set of bosons and fermions, and if you modify the BRST operator with this type of coupling, the extra terms decouple. The dependence on these fields decouple from the cohomology. Now I remember. So the point is, this action here, this term here, can be written as Q of something. That's right. So it's Q of S d bar lambda bar, okay, plus S hat. So it's a BRST trivial term you're adding, so in principle, it doesn't contribute to scattering amplitude. If all the states are on shell, it won't contribute. Okay, so, but if you don't do this, this object here is not manifestly Lorentz covariant. So your expressions would not be manifestly Lorentz covariant. So the advantage of doing this is it allows the computations at each stage to be Lorentz covariant. Okay, there's an additional subtlety which I will mention. So what about beyond 3 loops? So why did they stop at 3 loops? So there are these objects which sit in the denominator of the BGOS which start to cause problems if you have too many of them. So at 3 loops, it turns out they don't cause problems. But if you try to go to 4 loops, you'll find that these poles, at least nobody knows yet how to do correlation functions if you have too many powers of these poles. So that's why computations up to now have been just up to 3 loops. Okay, so the last thing I want to discuss is ADS 5 times S5 background. So that's interesting probably for people here. So okay, but are there any questions about this before I go to curved backgrounds? Yes? Okay, so we're solving this equation where Q is defined here. And I can sketch what the next term is. If you take, Q has 2 terms in it, lambda alpha d alpha and W bar R. If you commute lambda alpha d alpha with this, you get T. But now there's an additional contribution to Q from here. And because of that, you have to add a term here, which is proportional to R, which is going to cancel. So it becomes a cohomology question. I mean, there's a term here with 2 Ds and pi. And then there's another term with 2 Rs, another term with 3 Rs, and then it stops. Okay? So these are the 4 terms in the BGOS. I mean, I'm not sure exactly what your question is, but they can be explicitly computed. I mean, they have been explicitly computed. Okay, so this is a prescription for computing multi-loop amplitudes. It agrees with everything that's been computed using RNS, but of course it goes beyond what was computed using RNS. Okay, so now let me go to curved backgrounds. So we have the vertex operator here. This is the vertex operator for the open string. And now the vertex operator for the closed string is just a square of this, as it's always been. So it's going to start out with a term of the type d theta alpha, d bar theta hat alpha hat, a alpha alpha hat. It comes from the square of this to this. But then there are lots of other contributions coming from all the cross terms. Now you can combine these contributions in various ways, but it's clear you're going to have terms similar to what you had in RNS in a curved background. So we're going to have, I guess, this type of coupling and this type of coupling, but we'll also get couplings to the curvature. Okay, so that will come just from the cross terms of this with this. Will give you terms proportional to, so it will be a term of the type W gamma mn lambda, W hat gamma PQ lambda hat, R mn PQ. So this was, before this was psi, psi, psi hat, psi hat. But there's an additional couplings of this, of D with D hat, for example. Now, if you take the left-right product of W and with itself, remember the lowest component of W is the gluino. So if you take the product of the gluino with the gluino, I guess I erased it, you get the Ramond-Ramond field strength. So although it reproduces terms as in the RNS curved background, like this type here, there are new terms which don't appear in the RNS, which couple to the Ramond-Ramond fields. So remember, the RNS curved background was only defined for Nova-Schwarz. Okay, so W, I wrote down what A alpha is here. So AM, the AM superfield starts to lowest order with AM of X, and then it has the gluino to linear order in theta, and W alpha is a superfield which starts with the gluino to lowest order, and then the next order term, it couples to the field strength, to the derivative of the gain. Okay. So when I two of these, I get the Ramond-Ramond field strength. Which one are we talking about? That one there? Okay, so all of these, of course, are related. So I didn't tell you, I told you the relation of AM with A alpha. That's here. Now the W, I didn't tell you what W is in terms of A alpha, but W alpha is equal to gamma M alpha beta minus D beta of AM. So it's a field strength constructed from these gauge fields. In the same way as FMN is just DMAN. It's a field strength constructed from. That's right. Well, most general, sorry. So this V is a solution. QV is D of something. And that something is lambda alpha A alpha. So it's not the most general, it's the one which satisfies Q of it is equal to derivative of lambda alpha A alpha. So everything is, of course, determined in terms of A alpha. Any other questions? Okay, so let's go to the Ramon background. I'm sorry? Yes? Now I redo for, what do you mean redo? I'm not going to redo. What do you want me to? I'm writing down the curved background now. Yes? So this is the unintegrated one for closed. The integrated one for closed is going to be the left-right product of the integrated one for open. I don't know if that's what your question is. No, okay, so once you've done it for the open, you're essentially finished because the closed is just the left-right product of the open, both for unintegrated and integrated. Yeah, that's for unintegrated. I wrote the most general solution, and I found that it had the form lambda alpha A alpha. So this this thing here, V equals lambda alpha A alpha. So okay, so this is the most general massless solution. Then I looked for a integrated one, which I call V, which satisfies this identity, and that determines these terms here. So, okay, so I don't have to solve the cohomology problem twice, if that's what you're asking me. I mean, in some sense, okay, it depends on how you describe it. Okay, but is the procedure okay? Is people? Okay, so now let me tell you how to do Ramon background. So the vertex operator in the closed string, the integrated one, is essentially the action. So this is just going to be the action. So this is in a general supergravity background. But now we want to restrict to ADS5 times S5. So the nice thing about the ADS5 times S5 is that the metric in ADS5 times S5 can be described in a simple way in terms of a coset, which takes values in PSU224 over SO. So the relation between these is that you write GMN is equal to so this is now some metric which is a superfield. This capital M and capital N can either be vector or spinor indices, just like the indices on the Yang-Mills gauge field could either be vector or spinor indices. This small a and small b are tangent space vector indices. And these capital EMs can be defined in a simple way in terms of this coset in the following way. If you take G minus 1 dg, in general it will be some function of dx and d theta. So we can define So this capital M, as I mentioned, can either be vector or spinor indices. And if we take this coset here, and put this what's called a left invariant form, what you can do is you can expand this in terms of these dz's. Now this capital M ranges over the vector spinor indices, and similarly this capital A ranges over the Lie algebra indices of PSU224. So let me tell you what those are. So can either be the usual vector indices. So this is a vector. So there are 10 of these. It can be the 32 fermionic symmetries of PSU224. So alpha and alpha hat go from 1 to 16. Or it can also be the generators in the denominator of SO41 times SO5. So let me write these as AB. So this there are 20 possible values for these because there are 10 generators of SO41 and 10 generators of SO5. If you take G minus 1 dg, it takes values in the generators, in the Lie algebra generators of PSU224, and you can expand these in terms of the z's and write the action determine. So in an arbitrary curved background, you can write it in terms of the super Vierbeins. In this ADS5 times S5, you have the possibility of writing the action directly in terms of this coset. So that's only possible for PSU224 because of the isometries of PSU224. Okay, so what does the action look like? Thank you. So I'll just write down the action and then I'll. So in ADS5 times S5, of course, you have a which, because it's Ramond-Ramond, it has an index on the left movers and an index on the right movers. I guess I should put it. Oh, okay. So you have a coupling of this type. There's another term. In the opposite order. So these are the terms that are independent of the ghosts. And then you also get terms which couple to the ghosts. So I'll explain these terms. These terms here come from essentially writing EMA in terms of the coset. These terms here come from the ghosts in the same way. I guess I erased, oh no, here too. So if you take the left-right product of two of these, you'll get the curvature of ADS5 times S5 coupled to these ghosts. So this is the S5 curvature. And this is the kinetic term for the ghosts, where the spin connection is related to the spin connection of ADS5 times S5. Okay, so this is the action. You can quantize it. It's not so simple because G is some nonlinear sigma model based on this coset. But in principle, you can do computations by expanding example, in the large radius limit. So there's a factor of r squared in front. It's manifestly PSU to 4 invariant just because it's constructed from this coset. But, okay, as you can see, it's not as simple as in a flat background. So it's a challenge to be able to even write down vertex operators. In this language, some work has been done. For example, for the half PPS vertex operators, half PPS states we've written down the vertex operators. But computing scattering amplitudes involving these vertex operators is still an open. Okay, so I'll stop there.